Alright, let's start talking about combustion reactions. A typical combustion reaction starts with a hydrocarbon, as shown right here. Basically contains carbon and hydrogen with some specific amount depending on the molecule. Sometimes you might even have oxygen present in the compound. Elements such as nitrogen and the halogens could also be incorporated in here. But to keep matters a bit simple, we're going to stick to carbon hydrogen and carbon hydrogen oxygen containing compounds. And the idea is that when reacted with dioxygen, the hydrocarbon compound will yield carbon dioxide plus water. This particular process is not only known as a combustion reaction, but it's known as a complete combustion reaction, implying that enough oxygen is being fed as a reactant to yield full-on conversion of CO2 and water in the process. Right now, as you can see, the values for carbon and hydrogen, and in the case of the carbon, hydrogen, oxygen containing molecule, all of the amounts for the atoms are different. They are variable. And so we're going to use those values initially symbolically to balance this reaction. And the idea is that anytime you have a combustion reaction, you must start with a hydrocarbon, meaning that you have to have carbon and hydrogen in the starting reactant. The hydrocarbon is then reacted with dioxygen to ultimately lead to formation of carbon dioxide and water. Those are things that you need to remember, things that I will expect you to come up with as products when you look at the reactants of a combustion reaction. Okay, now in terms of balancing this, we're going to do this symbolically first of all. So you can see that you have X number of carbons on both of the reactants. So as far as balancing the carbons, we need to place an X in front of CO2 in order to balance the number of carbons. Looking at hydrogen, we have Y hydrogens on the left side of the equation, but we have two hydrogens on the right side of the equation. In order to make this work out symbolically, we first need to bring down the value of hydrogens down to 1 on the product side. In order to do that, we need to divide the product by 2. Since we still need to get a value of y for hydrogen, we're going to multiply the 1/2 by y in order to come up with the right proportion for hydrogen. Now, since oxygen is present in multiple molecules in the examples right here, we have to actually account how many oxygens we have on the product side and how many we have on the reactant side to ultimately come up with a balancing factor for the dioxygen molecule. So if you take the 2 oxygens of CO2 multiplied by the X amount of CO2, that will give us a total of 2 X's worth of oxygens coming from carbon dioxide. At the same time, if we have the 1 oxygen of water multiplied by its factor of y1/2, we end up finding out that there is 2x plus y1/2 atoms of oxygen which have to adapt to a total value of 2z oxygens on the left side of the equation, or alternatively a value of z oxygens plus 2n oxygens for the hydrocarbon containing oxygen. And the idea right here is that we are pretty much saying that the number of oxygens on the left side of the equation have to adapt to the number of oxygens on the right side of the equation. Alright, now what you then do is plug in the actual numbers and solve for z or n, as you will find out in a second. Now let me show you a typical example. We have CH4 reacting with O2, forming CO2 and water. Okay, so typical products of the combustion reaction, typical reactants. Now looking at this, you can look at it from the symbolic point of view. The value of X is just the number of carbons that you have in the hydrocarbon. The value of Y is the number of hydrogens you have in the hydrocarbon. So now we know that X has to be 1 and Y has to be 4 just by looking at the formula of the hydrocarbon. There, since we need Y over 2 for water, we divide Y by 2, which means that we divide 4 by 2, leading to a value of 2 as a balancing coefficient for water. And finally, for this hydrocarbon, we know that 2 times C must equal 2 times X plus 1 times Y over 2, which is what we have here in equation format. We know the values of X and Y, so we plug them in just the way they are. And we find out that 2z has to equal 2 plus 2, which is the same thing as saying that 2z must equal 4, or z itself has to be 2. Now in essence, the values of x, the value of y over 2, and the value of z are the balancing coefficients that need to go in the equation. So as you can see here, it's a little bit overcomplicated to do it this way, since we have a relatively simple example. But let me show you something that looks a little bit more funky, where the actual algebra might help you out, by writing out the steps as opposed to trying to do it all at once, by inspection. So looking at this example, the value of x for carbon is 20, the value of hydrogen is 38, and the value of z is equal to 11. Alright, so we're going to input all of that stuff right here. X is 20, y 38, y and a half is 19, and z is 11. Alright, then the total number of oxygens. We have z on the first molecule, we have 2n for the second molecule. That's all that's on the left side. On the right side, we have 2 times x and 1 times y over 2, which is all on the right side. Here we need to input the values of everything that we know. We know the value of z, we know the value of x, and we know the value of y. So we're going to input all those values the way they are. Alright, so now we have 11 plus 2n equals 2 times 20 plus 38 over 2. 2 times 20 is the same thing as 40, and 38 over 2 is the same thing as 19. 40 plus 19 is the same thing as 59. If we subtract 11 from both sides to isolate for 2n, we have 59 minus 11, which is the same thing as 48. And if we divide finally by 2 to isolate for the value of n, we find out that n is 24. And now that we have the value of n, the value of x, and the value of y over 2, we have actually balanced the equation. All that needs to be done is to input the values into the balanced equation. Alright, so here we have it. Alright, so that does it for the combustion reactions. We will stop at this point. Thank you.